right. The next topic that we have, which is going to be a brief introduction to this, we'll come back. I guess not brief introduction, but we're not going to be finished with conservative vector fields. We're going to come back to it. And there's a whole section dedicated to them in 16.3. But for now, we're going to learn and take a look at this first definition here. Definition 6 of a conservative vector field. So effectively, conservative vector field just means that the vector field capital F, it is the gradient of some scalar function. So in other words, it's the result of a derivative. It's the result of a gradient. So, for instance, it's sort of like saying, okay, take the function 2x from Calc 1. Can you think of a function that when you differentiate it, you get 2x? Yes. The derivative of 2x is 2. Or excuse me. The derivative of x squared is 2x. So in this sense, we kind of are saying that this is a conservative scalar field. We don't use that terminology. You didn't see it in Calc 1. We don't use it now. But really, that's what we're saying. Effectively, does this quantity, can you find sometimes it's called a primitive. Primitive meaning coming before. You're more familiar with the term antiderivative, at least here at MSU. Some people do use the term primitive. So we're really trying to find a primitive or an antiderivative of this given thing. So again, we don't use the term antiderivative, we use the term potential function. So in this case here, if we line things up, we would say that this is conservative and that this is the potential function for this. Now again, we don't use this terminology a ton in Calc 1, like not at all. I'm only drawing this comparison to sort of make this idea and these terms not so foreign. Okay, well, let's take a look at example 4. Verify that this function, xy plus yz squared, is a potential function for the vector field f. Well, going back up to the definition, the gradient, so f is a scalar potential function for f. So this is true if the gradient of this equals this, then we verified it. So let's check. What is the gradient of f? Well, it's a function of 3 variables, so the result should be a 3-component vector. The x component is y. The y component is x plus z squared. And the z component is 2yz, which does match the vector field f. Check. So I'll just summarize and say, therefore, f is conservative and f is a potential for it. Lastly, we've got 2 theorems. Theorem 1 says that there's really these 2 different settings here. There's the 2-dimensional and the 3-dimensional case. In the 2-dimensional case, if a vector field capital F is conservative, then what I'll say here, the mixed or cross partials condition. So that's when I say mixed or cross partials, I'm referring to this. So notice here that F1 is the x component, but we're taking the partial derivative with respect to y. And over here we have f2, the y component, but we're taking the x partial of it. So in that sense, we call this the cross partials condition. So if our field's conservative, then this is true. And a higher dimensional version of this is if this three-dimensional vector field is conservative, then the curl of f is 0. Okay. So really quickly, I want to comment on this and just say, what is the curl of this vector field? Well, the curl of this vector field is right over here. Right here is the curl of a vector field, f1, f2, f3, just like we had on this page, f1, f2, f3. So over here, notice that if, let's go ahead and erase some of this so we can talk a little bit. So the claim is, if this vector field f is conservative, then the curl of f, which is this vector, then that must be the 0 vector. Now remember, the 0 vector is the vector where all of its components are 0. So what this is saying is that each of these terms must equal 0. Well, what's that imply? Well, that means that if two things, when they're subtracted, are 0, that means those two things must be themselves equal. And do you see how this right here is the two-dimensional? If we go back to the previous page, this is the two-dimensional criteria, or consequent. And that exactly repeats over here. We don't have these other conditions in the two-dimensional case because each of these terms has an f3 and a z in it. But if we have a two-dimensional vector field, there is no notion of a f3 or a z. That concept doesn't exist in 2 dimensions. So that's why the 2D case doesn't have these terms. But the 3D case does have all of them. So those two, although these two conditions look very different, they are actually pretty much identical. All right. So remark 5 is not a theorem. I'm sorry. I said 2 theorems remaining. There's only 1 theorem remaining. Or there was only that 1 theorem. Remark 5 is that for a 3-dimensional conservative vector field, the curl of f equals the 0 vector, which is equivalent to this, and this is exactly what we just talked about.